Hello and welcome to Team Wing It's Concept Design Final Presentation. Team Wing It was created through Oklahoma State's Applied Aerodynamics class, where we chose to do the project over Supersonic's small, unmanned aircraft vehicle. Our team is made up of 9 members, who can all be seen on the left.
So now that we've introduced the group, let me tell you a little bit about the requirements of the mission at hand. So this aircraft must be capable of flying supersonically for over 60 miles, all while weighing less than 55 pounds using a commercial gas turbine engine. The chief payload for this aircraft is a high-resolution FMV camera. This aircraft must also be able to maintain flight through zero visibility using autonomous autopilot functionality. In addition to all these requirements, it must also be up to date with all FFA standards, including the CFR Part 107 certification rules, and all electronics and propulsion systems must be existing and in service by 2021. The mission profile for our aircraft can be seen on the image to the left. In addition to the requirements shown on the last slide, there are also several performance requirements. The aircraft must be able to be launched and be recovered in an area of 25 by 25 feet. And in addition, operating costs should be minimized throughout the process of this flight. Throughout the entirety of this presentation, we're going to talk to you a little bit about how we not only meet, but exceed each and every one of these requirements at hand.
The targeted client for our supersonic UAV would be the United States military. The use for the military would be for surveillance, whether international or domestic. The United States military is the major contributor in research and milestones in breaking the supersonic barrier. National emergencies escalate within seconds. A supersonic UAV could be a response to these crises. Also, we would advance our abilities to have surveillance on a country when or wherever due to size and speed.
Next is our design. Here we constructed a model using some of our case studies that helped with our preliminary designs. Some of these case studies we went over were the North American F-100 Super Saver and Boeing Scan Eagle. This helped produce our final model with several other information about our materials and more information about the layout to follow.
Cost feasibility. Breaking the sound barrier is very expensive due to the fuel consumption. For example, supersonic passenger jets burn 3 to 4 times as much as a commercial airplane. But since our aircraft is less than 50 pounds, it would not require as much and would not be as expensive as a fighter jet currently in use by the military. For example, the weight of a fighter jet used by the military weighs about 34,832 pounds for max takeoff weight, while our supersonic UAV weighs less than 55 pounds. This would allow us to use less fuel and for the cost to be less for the military.
Our UAV is capable of breaking the sound barrier. Let's dive into the aerodynamics behind this. Our design consists of a high sweep wing with a span of 1.67 feet and a planform area of 1.25 feet squared. We have a high sweep wing with a low aspect ratio. Our design consists of a NACA 64-206 airfoil. Our aspect ratio is 2.22 with a sweep of 40. Having this high sweep reduces wave drag at transonic speed and also creates a lower weight. And we are able to cruise at supersonic speeds and level flight. Our cruise altitude is 20,000 feet with our max ceiling being 40,000.
Now, after finding an engine we liked, we went with a rocket to add on to this instead of a double configuration engine, and thus we kept our weight down with a higher supersonic speed, which is perfect for what we were looking for. Next was finding a propulsion system that worked with breaking the sound barrier. This was found using a turbojet engine. In doing so, this had to go supersonic speed while still maintaining a reasonable weight, thrust, and fuel. This exceeded no more than 1.1 Mach number and went to an altitude of about 2,000 feet, which was perfect for what we were looking for. Now, Still looking at propulsion, the turbojet alone only received 400 newtons of power, but adding the rocket showed that we could still go supersonic speed the entire travel time, and is now seen in the thrust curve on the PowerPoint.
Here, our aircraft needs to be below 55 pounds with an average weight just under the maximum. This was successful for our group. Where you can see the diagram is some of the placements of the devices and the sizes. Aircraft had several parts that had to be configured into this design as seen above in the layout of everything, where a requirement was that all of the electronics and propulsion systems used needed to be in service by 2021, and this was met when researching all the parts used. Some of the weight going into our aircraft is the material we selected, the first being carbon fiber, which was chosen for the shell of the aircraft, the next being titanium, which was chosen for the supports, and a thin layer of paint, being orange and black, was applied to a chic look to our aircraft, along with a thin layer of protection.
As mentioned in the previous slide, all of the structural supports for our aircraft are made of titanium. The first of which type are the circular ribs that are reinforcing the fuselage at every half foot. Next, there are airfoil-shaped and lateral support spars in the wings and the tail supports. In addition, there are titanium torque rods for the servos that are used in the ailerons and the tail flaps.
The high-resolution FMV camera we chose was the continuous rotational turret gimbal. This camera was lightweight with a long video range, allowing for surveillance needs. It provides the aircraft with a greater range due to its pan-tilt-roll camera control for wide-angle view. It also has a 30x optimal zoom that provides 1800p high-definition video with a 45 kilometer video range. The camera will ultimately be located at the bottom and at the center of the fuselage. That way, nothing is blocking its view.
As mentioned previously, the aircraft must have autopilot functionality. The autonomous autopilot system that we chose was the Farco MAP-14. It was chosen because of its equipped barometric pressure sensor, 3x accelerometer, and 3x gyro. The ground control that was selected was the desert rotor, shown on the left. Through the desert rotor, you can see first-person video from the aforementioned camera, and you can also work directly with the software that comes with the Farco autopilot system.
Of course, our unmanned aircraft vehicle had rules from the FFA we had to follow. Some of these rules from Part 107 are seen below. And yes, our aircraft meets all of them.
As shown on the right, in order to minimize our required takeoff distance, we decided to launch our UAV from a pneumatic launcher system. The launcher system that we chose can accelerate a 60-kilogram aircraft to a maximum velocity of 52 meters per second. In addition, it can operate in any conditions, and it can be set up in only 15 minutes. In order to ensure that our aircraft stops within the 25-foot by 25-foot box, we've designed a two-net recovery system. The first net is a looser, more bungee-like net that's designed to help flex and to help reduce the shock put on the aircraft, whereas the second net dampens the impact and ensures that the aircraft is caught within the required space. Throughout the entire design process, we put a big focus on minimizing the operating cost, which I would say is probably pretty attractive to a potential consumer like you. Because of our lack of built-in landing gear, the structural wear during our landing process was minimized, as was the need for repairs throughout the entirety of this aircraft's lifespan. Because of the lack of repairs, the main operating cost is due to fuel consumption, and because of how light our aircraft is, it only requires about 3 gallons of jet fuel per trip.
If you believe that Team Wingett's unmanned supersonic UAS is right for you, please contact 8675309. For purchase inquiries, hurry now. You wouldn't want to miss Wing It Thon.